Hi guys, welcome back. Today we're going to look at one more property. We studied the other properties in the last video. This one gets its own video. It's a little more complex. This one today we're going to take a look at the closure property. Our objective is to be able to identify the closure property for a set of numbers. So we'll get some definitions down so we know what we're talking about, and then we'll do a couple examples here. So the closure property simply states that if you're performing an operation on a set of numbers, meaning I give you a set of numbers, it could be whole numbers, it could be integers, it could just be a few numbers that I've given, that varies problem to problem. But a set of numbers, if I can perform an operation on any two numbers in that set, and I always result in a number that's in that set, we call that set closed under that operation. I know that's a lot of words. I feel like this makes a little more sense with examples, so we'll move on. So what is a set? It might help if we know what we're talking about in a set. What I'm talking about here is a given group of numbers. For example, if you have a set of china, it means it's all the same. You know what belongs in it. It came in a box. I told you there's 4 plates, there's 4 bowls. It's a given thing. So here we're talking about a given group of numbers. And then we need to determine if something is open or closed. So if you'll notice here we have a lovely farmer. He left his gate open. Now you'll notice there's horses in here. There's horses running around crazy out here. So if something is open, it means it can go in or out. There's something outside of it. If something is closed, here you'll notice all of the farmer's horses are stuffed in this stable because it is it's closed. So when we're talking about sets, that's kind of what we're looking at as well. Closed means everything stays within this little box that I've given you or this set that I've given you. If it's not closed, it means we might wind up with something outside of that set. All right, so how are we going to test for this? Well, there's just 3 steps you need to take. So the first thing we're going to do is identify the set of numbers. So for example, I might just say, is the set of integers closed under addition? I've told you all the information in that question. You just have to go back and pull it out. So what is our set of numbers? There I said integers. And what's the operation? That was also given. Second thing, you're going to choose 2 numbers from that set. So I said integers. You can pick any 2 integers you want. -2 and 4, -7 and 13. Anything that falls within that category, pick 2 of those numbers. Then perform the given operation and check for closure, meaning is your answer still within that set? So if it were integers, are they closed under multiplication? Just pick 2 integers and multiply them. -2 times 7 is -14. -14 is also an integer, so it could be closed. We don't know, we only did one example. However, if I came up with something that was outside or not within that set, then I would have what we call a counter example. If your result falls and it's not in that set, you have a counter example, meaning it's not a closed set. You found a number that it didn't work for, or a set of 2 numbers in the set that it didn't work for. So let's take a look at some problems here. This one's already done. So here we have our question. Is the sum of 2 odd numbers always an odd number? So what is my set? Well, we're talking about odd whole numbers, meaning not the negative ones. It can only be on the positive side. So my set is odd numbers, and I've given you some examples there. 1, 3, 5, 7. It keeps going and going and going. When we do our test, we can pick any 2 that we want. Under what operation? Sum. Sum tells me that it's addition. So under the operation of addition, is the set of odd numbers closed? Well, what that means is I'm going to try it. So I've picked 2 numbers. I randomly picked 3 and 7. You can pick whichever ones you like. When I add 3 and 7, you'll see that I get 10. Is 10 an odd number? No. 10 is an even number, which means within my little box here of odd numbers, 10 would be outside of this box. Why? Because it's not odd. It's even. So it does not fall within my set. 10 is not an odd number, so what I have here is our counter example. I've done a problem, I've wound up with a number that's not in the set, so I know that this set is not closed. I can say that with certainty because I have a counter example. We can't always say for certainty that a set is closed. We're just going to say we think it is based on what we can see because we haven't tried all of the problems. So this one we're going to work through together. So is the set of whole numbers closed under addition? So step 1 tells me to identify my operation and my set. The set of, well, it tells me whole numbers. So my set is whole numbers. What does that include? Well, that includes anything, I'm going to draw my little box here, from 0 on up. Whole numbers. And it wants to know if they are closed under addition. So how am I going to figure that out? We're just going to pick a couple and give it a shot. So let's do 0 and 2. I get 2. Is 2 a whole number? Yes. So this could be closed. We could try a couple more just to check further. 3 plus 7 is 10. That's also a whole number. 2 plus 9 is 11. It's also a whole number. What you want to do is you want to sit and think, is there any way that I can add two whole numbers together and get a number that is not a whole number? And the answer is no. So this one, we could say, is a closed set. Or we could say it could be closed, as we haven't tried every possibility, and that would be impossible. But this looks like it's a closed set. I can't think of any way to add two whole numbers and get something that is not a whole number. So let's try another one. Is the set of whole numbers closed under subtraction? So again, the first thing, what is our set? Well, it's told me whole numbers. So same numbers we were working with last time, meaning 0 on up, whole numbers. Under what operation? Well, this time it's asking me for subtraction. So, whole numbers, what's a few we could put in here? 9, 27, 3, 17. We could pick anything we want. That's a whole number. 0. Obviously, I can't put them all in there. So we're going to pick a couple and see if we can figure out if this is closed under the operation of subtraction. Well, let's just try 9 and 6. 9 and 6 gives me 3. This fits within my box. Does that mean that's closed? Not necessarily. We want to see if we can come up with an example that shows that this is not closed. So basically, how am I going to wind up with something that's not a whole number? Well, that means I either need a fraction, a decimal, or a negative number. Well, there's no way I can subtract these to get part of a whole. So let's see if there's a way that we can subtract something that might give us a negative number. So let's look at this the other way. What if I flip my numbers around? What if I try to take 9 away from 6? Well, 9 is bigger than 6, so I'm obviously not going to wind up with a positive number. When I subtract those, I wind up with negative 3. Negative 3 is not a whole number, it's an integer. So this does not fit in my box. Negative 3 is out here. It is not a whole number, it's an integer. So that means that this is not closed. So that's what we want to do. We want to see if we can come up with a counterexample. Don't just try one and say, oh, you know what, it worked, it's probably closed. Because I could subtract a number of different whole numbers and wind up with answers that are whole numbers. However, there's a way that I can subtract two whole numbers that I wind up with something outside of what I'm looking for. So that's what we're looking for with our closure property. Is there a way that I can get a number outside of this little closed pen that means it's not closed? All right, our last example, I erased part of my word, is the set of integers. So here's our set, closed under division. So, integers. And my operation was division. So let's think about integers. How did we define integers? Integers were whole numbers and their opposites. So, within our box, if we want to pick a few examples, we could have negative 3, 0, 4, 72, negative 99. You could keep going and going to fill this box, but there's a few examples. I have some negatives, I have some positives. What doesn't fall into the category of integer would be fractions or decimals. So basically I want to see, is there a way that I can divide so that I will not wind up with an integer? So think fractions and decimals. Is there a way that I can divide something that I won't wind up with a whole number? Well, let's take a look. What if I take -3 and I divide it by a number bigger than itself? 4. Well, if I do this division, I'm going to wind up with a decimal. And actually what you'll wind up with is -0.75. Or you can leave it in its fraction form here. But what you'll notice is this is not a whole number or a whole number's opposite, because this is part of a number. Whole numbers imply that they're all there. This is a part of a number, so this would not be a whole number or its opposite, which means it is not an integer. So this would not be closed under division. The other operations it would be closed for, but division doesn't work. So again, remember when you're doing this, you just want to look at what way can I make this not work? Is there any way that I can take my numbers and perform this operation so that I'll wind up with something outside of this box?